Hello everyone, my name is Parth Gupta from section A5. Today I will be presenting a very interesting and important topic from quantum computing: classical deterministic, classical probabilistic, and quantum probabilistic system with example. These three systems types are fundamentals in understanding how computation has evolved from predictable machines to unpredictable machines yet powerful. Simple question: what exactly is a system? In computing, a system is any structure that receives input, processes it, and gives output. This can be represented as a flowchart: input, process, output. Now, system can be of two types. It can be predictable, where we know exactly what will happen, but it can be unpredictable, where outcomes may vary. Let's take a very simple example: a vending machine. You insert money, which is an input. The machine checks the amount, which is a process, and you receive your snack. This is the output. So this is a predictable system. The same input gives the same output every time. Like if we put rupees 10 in vending machine, uh, always it will gonna show rupees 10 you had inserted. Type of system we look at is classical deterministic system. In deterministic system, the same input will always result in the same output. So there is no randomness involved. Everything is fixed and it is predictable. Let's look at some examples. Calculator. If you enter 5 plus 5, you will always get a 10. Digital circuits and AND gate always gives 1 when both inputs are 1. No exception. It's fixed. These systems are used in simple digital devices, logic-based computing, and traditional machines where predictability is necessary. While these systems are easy to model mathematical and behave exactly the same way every time, which makes them reliable but not flexible for complex or uncertain problems. So it have benefits but have some disadvantages also. Let's talk about classical probabilistic systems. These systems introduce randomness, but in a controlled or simulated way, we can say. This means that even if you give the same input, but the output may be different each time because the system uses pseudo-random numbers internally. A very common example is a roll simulator. Every time you press roll, you may get a random number between 1 to 6. The input is same roll, but the output is random, which can lie between 1 to 6. Another example is a biased coin toss. The probability of head should be 70% and tail 30%. So the system does not behave the same every time, but it's still following predictable probability rules. These systems are useful in simulations, gaming, AI models, and environment where uncertainty is a factor but still needs to be modulated logically. Now we move into the most fascinating part: quantum probabilistic systems. These systems are governed by the rules of quantum mechanics, which means randomness is natural, not stimulated. Like randomness is still there in classical probabilistic system, but at some point it is stimulated. We are predicting it. But in quantum probabilistic system, it is totally natural. Like in classical systems, a bit can either be 0 or 1. But in quantum system, a qubit can be in both states, 0 and 1 at the same time. Like for जैसे कि जो क्लासिकल डिटर्मिनिस्टिक सिस्टम था उसमें जो क्यूबिट थी बिट थी वो 0 और 1 में से एक ही हो सकती है, लेकिन क्वांटम प्रोबेबिलिस्टिक सिस्टम में वो एक ही टाइम पे दोनों हो सकती है और इस फिनोमेना को हम बोलते हैं सुपरपोजिशन. However, when we measure a qubit, we only see one of the states, either 0 or 1, and the probability of seeing either result depends on the quantum amplitude. Another key concept here is interference. Unlike classical probability, where probabilities just add up, quantum amplitude can cancel each other due to interference, leading to outcomes that are completely different from what classical intuition would predict. These systems are powerful because they can process multiple possibilities at once, which is why quantum computers are promising for solving complex problems like cryptography and optimization. Let's move on to system comparisons. So जो आउटपुट टाइप रहता है क्लासिकल डिटर्मिनिस्टिक सिस्टम में वो फिक्स रहता है while in classical probabilistic and quantum probabilistic it can be random. जो randomness रहती है वो क्लासिकल डिटर्मिनिस्टिक सिस्टम में नहीं रहती है लेकिन क्लासिकल प्रोबेबिलिस्टिक सिस्टम में होती है but it is stimulated while in quantum probabilistic system it's totally natural. स्टेट बिफोर आउटपुट हमारा रिजल्ट आने से पहले ही हमें क्लासिकल डिटर्मिनिस्टिक सिस्टम में मालूम होता है कि इसका हाँ अगर हमने ये इनपुट दिया है तो इसका आउटपुट ये आएगा. Even in at some point classical probabilistic system we know the output but it can vary while we cannot predict the output in quantum probabilistic system. Physics base it's classical while quantum probabilistic system is based on quantum. For example, calculator is an example of a classical deterministic system. As we had already discussed, 5 plus 5 always gives 10. While the example of classical probabilistic system is dice stimulation like rolling of a dice or guessing of weather. So it is stimulated but it can vary. While the example of quantum probabilistic system is qubit or quantum key we can say. Now, let's look at the mathematical model behind each type of system. First, classical deterministic system. The state is represented as a vector of a number. Transitions are defined using Boolean matrix, meaning the matrix contains only zeros and one. Like we can define it using a matrix which can contain only two digits, either it will be 0 or 1. For example, marbles moving through a fixed path. Like if we are moving a marble but it can be moved only through a fixed path, we cannot change its path. Classical probabilistic system. Here the state is a probability vector representing the chance of being at different position. Transitions are defined using doubly stochastic matrices where each row and columns adds up to 1. Example, a marble has a 1 by 6 chance of being at a vertex A and 1 by 3 at a B and so on. Now, quantum probabilistic system. The state is represented by complex numbers, not just real possibilities. There can be complex possibilities or we can say imaginary possibilities. Transitions are governed by unitary matrices where the total probability modulus squared of amplitude is always 1. A unitary matrix allows reversibility, meaning if we had done a operation, we can undo it, which is a unique feature of a quantum systems. While the classical system does not provide these features, if we done a operation, we cannot undo it in a classical system, but we can do in quantum system. Now, to summarize, deterministic systems are fixed and predictable, while classical probabilistic systems use randomness, but what we can say that it use randomness but in a controlled way, like using through pseudo-random generators. It's totally not natural, it's stimulated. But in quantum probabilistic systems, the output are based on real, natural randomness from quantum physics, and it also includes the concept of superposition and interference. A famous quote by Richard Feynman sums it up beautifully. Nature isn't classical, and if you want to make a simulation of a nature, you better make it quantum. So this is the heart of quantum computing. It doesn't just simulate logic, it simulates nature itself. That concludes my representation. Thank you so much for listening. I hope you found it informative and clear. Thank you so much.